Alright, this video is kind of a combination of 6.2 and 6.3. 6.2, the overall goal is to find the area under a curve. In the last video that we did on 6.2, we didn't quite get to that point. So here we are going to be using that review to finally be tackling this objective to find the area underneath some sort of function or in some sort of curve. So what we're going to be doing in order to find the area underneath the curve is this process that we call limits of Riemann sums. But what really we're doing with that is we're going to be drawing rectangles. So here we go. I'm going to first tackle what we call inscribed rectangles, and let's say we have something of a function that looks like this. I'm going to call it quits here. We're going to just say I want to find or approximate the area underneath this curve. Well, right now we're just going to be approximating them, and let's say that I separate this. We're going to be separating these intervals into some sort of equal divisions. Okay, so I separated this into 3 equal divisions. We're going to be having to, since I want inscribed rectangles, we want rectangles that are within this curve or underneath this curve. So I'm going to have to use the pretty much what we would call the left-hand side of these divisions that I've done. All we would have to do is add up these areas of a rectangle, and then we would have the approximation of the area underneath this curve. If we want circumscribed rectangles, those are going to be rectangles that are drawn outside, so they can have pieces outside of our curve or outside of our region, separated into 3 equal pieces. So here are my divisions. Instead, you're going to find that I'll be using the right hand side of these subdivisions. So I'm going to use this line to draw my rectangles. And what's going to happen is you're going to get a higher estimate because these are lying, some pieces of this are lying outside of that curve. And that's okay, because for now we're just going to tackle how would we approximate it. Up here what you'll find is because there's some of this empty region here, then we're going to get a lower approximation. We once were deriving finding rates of changes, and so let's say, for example, that we had some sort of object that was at different positions over a period of time, and we use projectile motion functions a lot. And there's these things, these factors that work on it, that's going to be giving us the exact height over a period of time. So what we could do is we could take that position equation, derive it, and get the rate of change of that object, which the rate of change, as we all know, of an object moving would be its velocity. What's its speed? What's its velocity? And then what we could do further is we could find the acceleration. So now, let's say we know acceleration. Well, what integration allows us to do is work backwards. We can then find the velocity and the position because they're all related. So let's just look at the acceleration equation here real quick. The acceleration of any object that's flying through the air is actually always negative 32 feet per second squared. As long as we know that, what we should be able to do is find the velocity of that object. The integral of negative 32, and then we're going to integrate it with respect to x. What I do hope you could see is technically we have an x to the 0. Otherwise we had a property that if we are ever integrating a constant, what happens is that you just have to tag on that variable that we're integrating with respect to. Otherwise, if you would see this, you would add 1, divide by 1 because that's the new exponent, and still we're going to get negative 32x. And then don't forget we have to add that constant of integration. So now what we're looking at is, and I am going to call this c sub 1. So here we go. I'm going to break this up into piece by piece because that was one of our properties, plus, and then c sub 1, this is a constant. So that's one of those ideas where if it's a constant and you're integrating, you have to tag on another one of those variables, and then plus c sub 2. So finally what I get here is, and I'm going to just, for the heck of it, instead of calling this c sub 1, call it v, v sub 0, b sub 1 of x, plus, and then we're going to call this, I can't even remember what we called it, I think s sub 1. Okay, and right here I hope you recognize this. This right here is our projectile motion function. Alright, so now getting into the new stuff. So how is this integration all connected to finding areas underneath the curves? Well, what it actually allows us to do, not only does it allow us to do something like this where we work backwards, and what it also allows us to do is find the areas under the curve. And to understand this, what we're going to have to look at is first we're just going to start approximating the area of a region under a curve using what we call a Riemann sum. And this right here is the Riemann sum. Because of our review, you know what this sigma means. You know that this means that we're starting with 1 and we're ending with some sort of upper bounds. The things that you don't know really, we have some sort of function. All right, we're going to have some sort of function times delta x. And right down here I've told you what delta x is. This is our change in x, or when we're doing these, and when I was typing this should have an n there. We're going to be looking at rectangles to approximate the area under a curve, and the width of those rectangles, the width or the change in x, is going to be given by this equation right here. Also, the thing is, I didn't define what c sub I is, but what c sub I typically is, it's just delta x times and then our index variable we call I. So this is not always the case, and we're going to be looking at different types of these, but this is in most cases what you can use. So our goal, it's written in blue up here, is to approximate the area under f of x equals 3x over the interval 0 to 6. So what I do want to say is right here we're going to be drawing our bounds, and what we're trying to do is we're trying to find all of this. Eventually we're going to get into curves, and we won't be able to do some sort of geometric equation. So this is, for now, we're going to start out with the basic. So in order to approximate the area under some sort of function over the interval from a to b, so from 0 to 6 in this case, we're going to be using this equation right here. I'm going to let n is the number of divisions that we're going to be making. And here you can see here, for now, when we're approximating these, you can choose n to be whatever you want. I'm going to specify for us right now that I want n to be 3. Okay, so what that's going to amount to is something like this. There are my lines. I am going to use circumscribed rectangles. What we're going to be using are the right-hand sides of these subdivisions that I've drawn. So what you did notice is I gave you a formula that delta x is equal to my upper bound minus my lower bound, so the far right minus the far left, over n. And n, once again, we decided to separate this into 3 pieces. We've decided to separate this region into 3 chunks. So what's going to happen is we're going to get the width of our rectangles is 2. And I hope you can see that right here. The width, this is a delta x, this is a delta x, this is the change in x. Right here what we're saying is the widths of our x's are 2. Alright, now that we have our delta x, or in other words the widths of these rectangles, what we're trying to do is we're using this Riemann sum right now to add up the areas of our rectangles. So we have the width, this right here is the width. What we need to do is find the height. So I'm going to draw this out for you. The heights that we're interested in are happening at these right endpoints that we've decided to use. So basically, because the widths are separated by these delta x's, which are by widths of 2, what I'm really interested in is the f of 2, the f of 4, and the f of 6. So I'm going to write this out and just kind of let you kind of think about this for a second. So the area of the first triangle, the area of the first rectangle, we're going to call it a sub 1 plus a sub 2 plus a sub 3. It's going to look something like this. We need the height, which is going to be this 3. This is the function that gives us where these points are, the y values of these points. So what we're going to need is 3 times 2, and then that's the height times the width, which would be 2. So there's the area of the first rectangle, plus this is f of 4, so in other words 3 times 4 times 2, and then plus this one right here would be f of 6 to get us the height of this actual y value, so we have, and then times the width. Alright, so in other words, if you can kind of see what's going on with this, um, this is basically our index number. We're still going to be using our Riemann sum from the index starting at 1 up until all the way 3. I am going to use the idea that I am interested in the x values, in the f of x values that occur at the ends of each one of these intervals. So that's where we could use that delta x times I is equal to that c sub I that I'm interested in. So right here, what this would equal is 2, because that's my delta x times my I. And that's going to get me these values that I'm interested in. So I'm going to go ahead and say we're using our function. This is f of c sub I right here. And then all of this times 2. Okay, so that's going to get me this right here. And what I really hope that you go ahead and see then, we can add these all up, or we can actually go ahead and solve this out, and then what we would get is an approximation. When we do that, we would get 72. So we would get 72, and if you were to just do a basic geometric exact find of the area of this, what it would be is 6 times 18 divided by 2, which would be 56. But what you have to understand is, yes, this is very much over the 56, but it was to be expected because we do have circumscribed rectangles that we're using. We're using the same definition for approximating the area underneath a function. And I'm still going to let n equal 3 here. But what I'm going to do instead is I'm going to use inscribed rectangles. Okay, so here is the thing. When I'm setting my Riemann sum up again, this is what I'm going to have problems with. It's 3 times c sub I, and I'm going to have to calculate what my c sub I is. So same thing here. My delta x would be 6 minus 0. It's once again 2. Nothing has changed about that. But the idea is we're not interested in these end marks anymore. What I'm really interested in is the height of the first rectangle would be given by what is f of 0, what is f of 2, and what is f of 4. So c sub I are the x values that are going to be giving my heights when I plug it into my original function. The only thing that's different here is what you'll notice is what I was going by was 2's because of that delta x before. So I mean it was that delta x times each one of those rectangles that I was interested in. So I had 2 times I, but I'm not starting there any longer. So what I do have to do is take off one of my delta x's. So take off one of my 2's. So what I get is 2I minus 2. What I can go ahead and change that to be is 2 times I minus 1. What I did in the end was I took delta x I minus 1 because we need to be taking off a delta x each time. So in the end, my setup would look something like this. Okay, and then that's my function. That's the height of all my rectangles, and then times 2. Here's my width. So when all is said and done, what it would look like is something like this. Right, this is the area of my first rectangle plus, and then we have 3 times, that's the height of this rectangle right here, and then times 2, and then plus, and then we have, and that is, here's the height, and then times the width. Here's the height times the width. And once again, height times width. So this was my third. And when you do all of that, what you will get is, and this is a lower estimate, it is a lower approximation, but that's because we used inscribed rectangles. This is going to be really quick as we head into the next video, but I need you to consider this. First we were approximating the area underneath the curve. Now we want to find the actual area under the curve, and this is what we're going to use. So everything's the same. This is kind of the Riemann sum, except we're going to be doing a limit of the Riemann sum, and this is what's going to change. We don't have a set n divisions. We're going to have to say that n go towards infinity? What if n went towards infinity? So I want you to consider that, and then in the next video we're going to explore that. And